Okay, our next speaker will be Stephen Goldfeder, who will be talking about private smart contracts.
Hi, I'm Stephen Goldfeder, and today I'll be talking about private smart contracts. This is joint work together with my advisor, Arvind Narayanan, and I'll be talking about the topic more generally and not necessarily focused on my own work, although I will at the end try to focus on my work slightly. And the idea is to try to give some sense to a very, very hyped area. And as well as I think there's a very useful collaboration that can happen between the people interested in working on private smart contracts and the pets community, and things that the two can learn from one another, and I'm hoping to kick that off in the discussion forum. So the first question is, what is a smart contract? Well, you have here two parties, but it could be any number of parties. We have Alice and Bob, and they agree to a set of rules. And they want these rules to enforce, to govern their relationship. So they encode these rules inside a virtual trusted third party. And that third party is trusted, one, to follow the rules, and that's basically it. This is a trusted third party that follows the rules of their interaction. Okay, and it allows for stateful contracts, which means you can come back to the third party a few times, and it will update its state, and it can do things based on previous actions. Now, smart contracts by themselves, that's a nice idea. You can have a computer that you trust, but where it really gets its teeth is when you add that to a cryptocurrency system, because now the smart contract can manage money, and in particular, it can enforce penalties and incentives, and here Alice can pay into the smart contract can hold some money, it can decide to pay Bob eventually. And the first point I'd like to make is that notion of smart contracts that I just given, where it enforces rules of interaction between different parties. I didn't say anything about outsourcing computation. And this is something that people often confuse, where they'll say, Ethereum is the world's computer, but it's terrible, because if you compare it to what you can do on AWS, I mean, it's so slow, but no one's actually going to Ethereum or to a smart contract system because they want to get an answer to a deep problem that's bothering them. They're not outsourcing computation. Instead, what they're really doing is they're trying to enforce a set of rules between them. The system may, as a way to do this, do the computation itself, but as we'll see, that's not a fundamental property. Some systems will, some systems won't. So as I mentioned, Ethereum is the sort of biggest, largest, most mature project on smart contracts, and Ethereum has a Turing-complete scripting language, which means, in theory, subject to pretty restrictive limits on the amount of computation you can do, but you can sort of do arbitrary computation, whatever you want. And it allows for stateful smart contracts, so you can store state in the blockchain and update a state. And the thing is, every node, Ethereum does do that thing where I said it's not really the point, and that's outsourcing computation. So you're not going to Ethereum to outsource computation because it's super expensive and it's not what you'd want to do, but the system does compute your function for you. So every node, everyone in the system can run your code and compute the output and verify its correctness. And that last property is a bit problematic, because from a privacy perspective, it means that if everyone can run your code, then all the code has to be public, and all the data that code runs on and outputs has to be public. So a system where your code is all out in the open and the system just runs your code is not going to give you privacy, and indeed Ethereum does not give you a notion of privacy. You can try to overlay privacy on top of it, but it becomes very expensive and infeasible to do that inside Ethereum. So how did we get here? So Bitcoin was sort of the first deployed successful cryptocurrency, launched in 2008, 2009, and Bitcoin includes a scripting language, but it's essentially a payment system. It's Alice can pay Bob and not do much more than that. Then there were sort of two directions that this area of research branched out into. On the one hand, you had projects like Ethereum that said, let's add a scripting language to that, a full scripting language, a better scripting language than the minimal one included in Bitcoin, so you can attach arbitrary conditions to your payments and say, I'll pay you if this condition happens, or we'll play some game, and at the outcome, at the end of the game, the winner of this game will win. And that's how the smart contract direction went. And then there were the privacy coins such as Zcash, also Monero, went in the privacy directions, where they super focused on payments and said, Bitcoin is a great payment system, but it doesn't give you privacy. Can we build a payment system which hides all the information, both the prices as well as the addresses, who's being paid? Can we build a payment system? And sort of now, it's the obvious direction, but there's an effort to merge these two and say, can we achieve these both simultaneously? And somehow have the smart contracts of Ethereum and the privacy of Zcash. And that's a very large, broad area of research, and it's not even that well defined, as we'll see. What exactly is this combination system? What are the properties that it would have? So what is a private smart contract? Well, obviously, it's a smart contract with privacy. And that's about it. But the thing is, there are several notions of privacy. What do we mean by privacy? Well, think of a program where Alice and Bob are computing some function, and they each have inputs potentially, maybe only one of them has inputs. So we can think about the privacy of the inputs, and we can think about privacy of the code. Now, you could also think about who are we trying to hide things from? Are we trying to hide things from Alice and Bob themselves, or are we trying to hide things from everyone else who's sort of watching the blockchain and lurking and seeing what Alice and Bob are doing? So in terms of the code, it doesn't really make sense to hide the code from the participants of the contract. You don't really want to participate in something that you don't know what it does. But you do potentially want to hide the code from external observers, so they just see a blob where Alice and Bob have a smart contract, but they don't know what they're doing in the contract. And in terms of hiding the inputs, that's well defined for both internally and externally. You can imagine a contract where the participants want to share the inputs with each other, and you can imagine and they only want to hide them from the external world. And you can imagine a contract where even the participants' private inputs are private, and they don't want to share them with one another. And now, to motivate this, I want to go through several examples. And these are toy examples, but examples that show the power of smart contracts and the necessity by different applications. And the first one is a Sudoku game. And it's a simple contract where Alice says, hey, here's a Sudoku puzzle. Can someone tell me the solution? I'll pay you for that. And Bob says, yeah, sure, I can tell you the solution. Great. Now, why do you need a smart contract for this? Because Alice wants to commit her money, and Bob wants to make sure that if he gives Alice a solution, that he actually will get paid. And Alice wants to make sure that if she pays, she's actually going to get the right solution. So a smart contract will enforce the code. So they agree on this set of rules, and they have a contract for this. Now, where might you want privacy here, mapping to the privacy areas we identified earlier? Well, on the one hand, you might want privacy of the payment details. That's sort of Zcash style, and you can inherit those properties. So we're not going to think about that in this talk. We're going to think about details of the contract itself that you might want to remain private. So the input here, Bob's input, which is a Sudoku solution, that you might want to keep private. Maybe Alice wants to know it, so you're not going to hide it from Alice, but at least from an external observer, you don't want to post this solution on the blockchain because then everyone learns it. And you can also imagine examples where it's a slightly modified contract where Alice says, I don't want the solution, I'll just pay you if you can prove to me that you know a solution, in which case Bob would even want to hide his input from Alice. The other thing you might want to hide is the contract's code. So even if we hide Bob's input, anyone can look at the blockchain potentially and say, hey, there's a Sudoku game going on here. I know exactly what Alice and Bob are doing. I know what's going on. And for Sudoku, this doesn't really seem like a major problem, but think about if they're doing a transaction in a regime where they're nervous about being censored and they're trying to get by some restrictive laws, and there actually is sensitivity not only in their inputs, but in what their relationship actually is. And here, if they're buying a Sudoku solution when playing Sudoku is illegal, doesn't matter about the input, the actual notion that they're playing Sudoku, the code of the contract itself leaks a lot of information. And these are sort of two ways where you might want privacy. Again, you can do this contract in Ethereum very easily. Just encode a contract that says, hey, give me a Sudoku solution, it verifies it, and it pays. That's fine, but we want privacy. So what can you do? Well, you can use zero-knowledge proofs for an example like this. Bob encrypts the solution to Alice and gives a proof that says this is the right solution. And in this way, Bob hides his input. And you can also, I'm not going to get into the details, but there are ways to use zero-knowledge proof systems such that the circuit itself or the code itself is actually hidden from everyone else. So Alice and Bob can agree to the rules, but nobody else can see it. And this is a simple example where only Bob has an input, and moreover, it's a stateless contract. There's no multiple rounds of interaction here. Bob presents a solution and takes the money. No state needs to be updated. Let's talk about a slightly more complicated example where there's a state. So now Alice and Bob are betting on a game of chess. And they encode their rules of chess in a virtual smart contract. And first they pay their money in, and that's their wager, and whoever wins the game is going to get the prize. So now Alice goes ahead and says her move, and the contract now updates its state. It says, hey, is it really Alice's turn? Yes, it's Alice's turn. Is this a valid move? It's a valid move, so it updates it. And then Bob goes ahead and does his move, and they continue doing this until the end where the contract pays out. Okay, So this is a slightly more complicated example because they both have inputs. But let's see, what type of privacy might you want in this example? Well, again, you're going to want privacy of the payment details, but we won't focus on that. You might want the moves and board to be hidden from everybody else. So no one looking at the blockchain should know the state of the board, who's winning the game, what's going on. And you also might want the contract code hidden. So not only can no one know who's winning the game, they don't even know that this is a game going on of chess at all. They just see a blob where Alice and Bob are doing something, and they don't know what's going on. Now, I want to point out here, the thing you do not want is the inputs being hidden from one another. That's clearly not a desirable feature, because if you're playing chess with somebody, you kind of want to know what their moves are. If not, you have an interesting game of chess meets battleship, and it probably won't end too well. Again, for this example, we can use zero-knowledge proofs. Each player proves in zero knowledge that they legally updated the board. That is, the proof takes a previous state, it takes a transition, which is their move, and it takes an end state, and it shows them that, okay, they prove that this is a valid move. Again, this is a situation in which we can get input privacy in this way, because they can not leak their moves to the blockchain. Instead, they commit to the code, and they just prove things about it. But let's take a look at a slightly more complex example where zero-knowledge proofs are not going to be a tool that works for us. Oh, sorry. First, are zero-knowledge proofs feasible? Well, the answer is they're getting there. The technology is progressing. Snarks are and that line of research is the most promising, but there are a few issues that need to be resolved first. First of all, these proofs require a trusted setup per contract, which means you have to do a trusted setup for every different contract code that you want to execute, and that's not really feasible to do that. They're also expensive, and the programming model uses circuits, which could be confusing for developers. Okay, but let's look at a different example where zero-knowledge proofs won't get us there. And that's a private auction, a very simple auction here where Alice and Bob are each going to say a price, and the higher price is going to win. Okay, so here Bob should win, and the contract says, yes, Bob won. And where might you want privacy in the auction? Again, you might want to hide the payment details that you always want. We're not going to focus on that. But you want to hide the bids. Alice doesn't want Bob to know her bid, and moreover, Alice and Bob don't want anyone else to know their bids. And lastly, again, you might want to hide the contract code. So nobody looking at this should have any idea that an auction is going on. They should just see this blob and say, something's going on here, I don't know what's going on. So certainly you want to hide the bids, and you also want to hide the contract code. And the interesting thing about this contract, which we didn't have previously, whereas in chess, you're not hiding the state from one another, here you do want to hide your bid from one another. Even after the contract, Alice and Bob don't want each other to learn their respective bids. So, do zero-knowledge proofs work here? The answer is no, because zero-knowledge proof allows you to prove something about computation that you did. So in chess, each person takes turn, and they can prove things about computation that they did on their inputs. Here, because the inputs both remain private, who's going to create the zero-knowledge proof? Someone has to compute the max of the two inputs, and that's not, there's no easy way to do that. There was a proposal, which was an earlier paper, it was called Hawk, where they said, okay, here's how you can do that with zero-knowledge proofs. Trust some manager, and this manager will be your privacy manager. He's totally trusted just for giving privacy. You give him the two auction bids, and he'll tell you which is the max, and then he'll give you a proof of correctness that he did the right thing. Now, that works, but it sort of misses the point a little bit because you have to trust the privacy manager. You have to actually give your input to someone, and that's not what we want exactly in a fully private system. Here's an example where you can use secure multi-party computation, where the parties jointly compute a function using different secure multi-party computation protocols, such that the inputs aren't really revealed, but only the outputs are revealed. The downside of secure multi-party computation, whereas it gets us what we want mostly, these protocols are expensive, they have rounds of interactivity, and if people drop out, it becomes an issue. And also, you don't get program hiding here. If you do secure multi-party computation, the inputs are hidden, but everyone knows, all the participants know exactly what function they're doing because the MPC protocol is defined based on the function. Okay, so very briefly, can we build private smart contracts without using any fancy cryptographic details? And there is one line of research that uses trusted execution environment. There's Ekiden, which is a paper, and there's recently a company launched, Oasis, and it actually gets you a lot of the way there. If you want to trust Intel SGX to sort of perform the computation for you, it gets you a lot of the way there, but the problem is, of course, the trust. You have to now trust hardware sitting in someone else's possession to run your contracts for you. And that has two problems of trust. Number one, you have to actually trust that the hardware is keeping things private, that there are no side channels, for example. And two, you have to trust Intel. Intel is is issuing attestation keys that the hardware is using to say that what it did is correct, and if you don't trust them, they can attest false things. Another approach is off-chain execution of contracts, and this is the idea where the parties do what they do offline. They just agree to compute off-chain, and they sort of go ahead and tell the blockchain, hey, we did this off-chain, and this is what happened, and this is the result, and we never tell you what happened. And the thing is, though, with off-chain computation, it gives you program hiding because you don't report the state of the VM on chain, but what it doesn't give you is input hiding, because all the parties know the state of the VM. And moreover, when there's a dispute, you run into a problem, because with the contract, the blockchain has to mediate disputes if the parties can't get to agreement. And generally, in a lot of these systems, what happens is you bring the computation on chain at that point. So you have privacy when everyone agrees and doesn't hit the blockchain, but when you hit the blockchain, you sort of lose privacy. So can we do things better in the case of a dispute? And this is a paper this is the piece of which is my work. We have a paper using an Arbitrum, which gives you an efficient proof system such that even if you have to go an on-chain dispute, you still have no meaningful loss of privacy. I'd like to conclude that private smart contract is sort of a buzzword, and depending on your application, there are a lot of different things that this can mean and different tools that you can use. These are all valid tools for valid applications, but they differ widely based on what you need. There's lots of ongoing work, and all of these works, nothing is perfect. There's lots of work to realize a real system that builds private smart contracts. And now the big question is, what are the applications? Assuming that we have these in the next several years, what can we do with these? So the killer application for Ethereum seems to be trading kitties with other people, crypto kitties, and can we think of perhaps better applications, not to put down that, can we think of other more useful applications for private smart contracts? And with that, I'd like to lead into the discussion. And just to set what I started with before was, I think that there are lots of ways where we can, we meaning people who develop private smart contracts, can learn from the PETS community, both in terms of what are the interplay of positive and negative aspects of private smart contracts, and what lessons can we learn from Tor. And there are also, on the flip side, things which I think the PETS community in general, even if you're not interested in cryptocurrencies, can learn about private smart contracts. In particular, if you think about this as a primitive, what nice and interesting things can you do with it, and how can you augment protocols that already exist? With that, I'd like to turn this over to the discussion. Thank you.
Okay, we have nearly 10 minutes.
Hi. So you're telling us there will probably be a primitive that's going to be built. What can you do with it? Isn't that a weird way to approach a problem? Like, shouldn't you first try to detect a problem that happens in the real world, and then try to see how you can solve it, rather than sort of building these amazing private smart things even without knowing what can be done with it?
Sure. I mean, that's a great question. And the first thing I'll tell you is, as I mentioned in the beginning, I'm not primarily presenting my work. I'm sort of saying this is something that's happening. There is, in terms of venture capital, literally billions of dollars being poured into industry in this, and there's lots of academics who think this is an important problem. If you read these white papers, everyone has their killer application, and some of them are good and some of them aren't. And CryptoKitties might be an interesting one, and it might not be. But the idea is this is something that's, irrespective of me, is happening. This research is going on. And I think that's a good question. People should think about their applications. But in terms of what this community can think about it, this is happening, and in the next few years, you'll have a private smart contract. So what can you do with it? And if potentially we think that there is no good application for it, it's still going to happen.
Steven here.
Hey.
Great talk, thanks. I had a question about, so you mentioned that you can have different privacy constraints. You can have the code should be private, the input should be private. How practical are the relaxed versions? So let's say I just want the inputs to be private. The code is out there. Everyone knows I'm solving the pseudocode. Are they nearly efficient?
Sure, and you said just the input's private, right?
Yeah, just the inputs.
Yeah, so for that, again, so the three main candidates for that are, one, using zero-knowledge proof system, assuming that it's just like a back and forth and there's no joint computation of a function. Mm-hmm. That's the actual running of the proof is relatively efficient, but the issue is doing the trusted setup, and in particular, all participants in the contract. The issue with the trusted setup is not actually the difficulty of doing the setup is the difficulty of getting trust in the setup, that people believe that this is not subverted. So Zcash, for example, has a single circuit. So they can go through the ceremony and take a year or less and get 80 to 100 people involved, and they'll get real confidence that this is not subverted. On a system that has one contract or one function, you can do that. On a system there, everyone's defining their own, and they might want wide belief in the correctness of their proof system, of their proof. It's a lot less feasible. Secure multi-party computation is relatively, it's becoming more mainstream and getting feasible. The issue is, which I glossed over, is for secure multi-party computation, there are still some model issues here. And who's actually doing the computation? Mm-hmm. So is it the parties themselves doing the computation? There are some systems in which the party sort of outsources. So I'll secret share my inputs to another set of parties, mm-hmm. and who I don't know, just nodes in the network, and they'll do the computation. And that has some negative aspects to it, because if these people are all malicious, then they can recover my inputs. But I think those are both feasible, modulo the trusted setup, but that's also something that the people are working on. There was a paper recently, not an efficient paper yet, but how to make a sort of a global CRS, common reference string, for these systems.
I see. And just one quick follow-up on that. Like, so for MPC, you said it's expensive and the overhead is too much. Does it come from the communication part, or the rounds,
Yeah, so one issue with the MPC is, well, first of all, MPC is it's using sort of more heavyweight protocols. Often MPC systems will sort of use zero-knowledge proofs to get malicious security, so it's whatever you have there plus in some cases. These aren't necessarily snarks, they're more efficient proofs, but also it's the multiple rounds of interaction, and so what goes wrong if someone goes offline during this, you have to start the thing again, and this can be a vector of attack for denial of service, for example.
It's also it's a different adversarial model, but once you look at semi-honest or not, or at least with the honest majority, I think a lot of these problems in the MPC domain start falling back. So
yeah, if you want to go semi-honest, for sure, then you're okay. I think semi-honest is a very useful model for designing protocols.
Yeah.
Then you sort of want to say, okay, how can we add zero-knowledge proofs to make these maliciously secure? I wouldn't launch a system in the semi-honest model.
Yeah, so hello. Nice talk, thank you. So my question is about the notion of privacy in cryptocurrencies and blockchain in general. So I think today we have several coins, several privacy techniques. They give different privacy notions, and even for experts, it's hard to compare them. Why, or to know whether one is more private than the other, or stronger or weaker. So I would be curious to know your opinion about, shall we take a step back and trying to make a common privacy framework, a common privacy notions that we can compare them and try to define them, and then compare them in terms of stronger, weaker security notions and privacy notions? In
terms of just payment systems, you mean?
Payments or contracts or different. I mean, imagine the two blockchains that support contracts or two blockchains that support coins.
No, that's definitely a useful thing to do, and it's something which I think. Right. What you're saying is absolutely true, and as I mentioned before, especially in this industry where everyone has their project that they're rooting for, and they have often lots of funding as well, and there's a lot of sometimes there's some toxic. It's a bit of a toxic community where everyone. Their project wins, where everyone else's project is worse, and it does become hard to get the truth, academic truth out of this paper, and it's something which I think is probably ripe for a systemization type paper. Definitely agree. I think actually Arvind, my advisor, and Malta have a workshop paper from a year or two ago where it's called Obfuscating Techniques in Cryptocurrencies, where they try to bring some sense to these techniques, not including they launch cryptocurrencies, not the positing about things that will happen. So that's definitely a good start, but definitely more work in systematizing this knowledge is for sure necessary.
Okay, thank you.
So whenever you have a bunch of private contracts, I think you're very likely to end up with lots of people being tricked and defrauded, and then they don't, of course, have anywhere to turn to because they won't have things to show. Is that what is your take on how that might proceed?
So the way I think about private contracts, there are sort of two models you can think about. There's the open world and closed world. So the ones I described here today are sort of in the closed world, And those are sort of the ones I'm focusing on. So you have Alice and Bob. So it's private in the sense that they're not leaking anything to everyone else. But they know the full state of the machine, or the full state of the code at any point. And in particular, they also have zero-knowledge proofs or some receipts in these cases of when things go wrong. And a good system, a really good system, the way that it should work is that the blockchain sort of figures out all these issues.
But just sort of, if Bob writes a contract that it's tricky because these things in Ethereum and the smart contract language, it could be very tricky to understand exactly what's going on, and he writes it in such a way that it looks good to Alice, but then it turns out there's a hidden thing in there that gets triggered, and boom, she loses all her money.
This is a real problem, but I don't think it's a problem specific to private smart contracts. It's a big problem. Code correctness in cryptocurrencies and Ethereum contracts is a huge problem, and we see like a parity bug where people are losing hundreds of millions of dollars because of a bug, probably unintentional. And I think it's a huge issue, but I'm not sure that the privacy model hurts that, considering that, again, Alice, when she signs on to the contract Bob wrote, she has full ability to audit the contract, to audit the code before she sends a dime to it.
But I guess if they're public, you could imagine some sort of enforcement mechanism where there's external parties monitoring things, and then Alice has somebody to turn to, right?
Well, this is, again, a huge problem in the area of what is this external, what are we agreeing to, and what is this external party? Because in some sense, we're agreeing to the code. And if there's a bug in the code, then who's the one that's privileged to say, oh yeah, this is a malicious bug in the code? Sure, that's true. And also in most of these systems, for example, in Arbitrum, there's a commitment to the full state of the machine on the blockchain, so Alice can go ahead and open that up for anyone she wants to and say, look, Bob tricked me. But you'd have to sort of include some mechanism for some privileged party to look at the code and say, yeah, you did exactly what the code said, but you put a malicious bug in the code. And that's a mechanism we don't have even in non-private smart contracts. We don't have that in Ethereum. There was a fork over what to do about the DAO hack. Should we compensate people for this? Should we not? And that's how Ethereum Classic was launched, over this debate. So this is a big problem, and I think when we figure out what that mechanism is in regular smart contracts, perhaps we can port it over to private smart contracts, but I don't see it as specific to this notion.
Hello, sir. You guys at Princeton are doing a really solid work.
Thank you.
On cryptocurrency and signature schemes and so on. And really solid work for freedom. And I'm very excited about private, dark, smart contracts and the possibilities that they open for new forms of human organization that were never, ever before possible in human history. And to finally apply our cryptography ideas in a way that's useful and empowering for all of humanity. But I have a two-part question. First of all, what do you think of Taproot and adapter signatures? And second of all, do you think that we can get maybe the better way for anonymous blockchain contract systems is maybe precompiled contracts with a proof that this contract was executed in some kind of limited way. For example, it's done with how they used the trick with the pre-images for the cross-chain transactions or the range proofs.
So I didn't get the last part of the question, sorry.
So for example, we can, when we're in more simple cases, we don't always need to use zero-knowledge proofs. We can construct simpler proofs to prove more simpler things. So if we actually make a conscious decision that we're going to focus on a specific subset of features and offer those as pre-compiles inside of the currency that gets switched on and off.
Yeah, so I'll sort of take the last part first. This notion of doing pre-computed features to sort of get around these definitely has some merit, although often, so I'm not sure about the system you're specifically referring to, you have in mind, but there are people that sort of they want to get around the zero knowledge proof problem by sort of having a bunch of different proofs that you can sort of combine in different ways, so you can now have a limited feature set, but that you can sort of tack them together in different ways. So from a complexity perspective, you have more proofs going on, so it's a bit larger, but from a trust perspective, if you can just do a trusted setup for these 10 components, and then you'll be okay. I'm not sure exactly if it will, it might be a lesser degree of privacy because you sort of won't necessarily be protected in how these components interact. So I'd have to think about how those systems work, and I don't have, without a concrete proposal, I don't know, but it's definitely a very interesting direction. There's a company called QED, and they, I think, are doing something along these lines of combining different pieces to make larger wholes that would be more feasible with zero knowledge proof. So definitely an interesting research direction. And in terms of these other signature, I'll say, hacks, and I don't say that in a bad way. Actually, I've done a lot of work in threshold signatures and thinking about how these can be used for private smart contracts. These are sort of very interesting and but still limited. The platform, for example, Arbitrum, is a general computation platform, and you can do tons of computation. Signature, like smart contracts, the ones that I'm familiar with, they generally focus more on not the computation that you're doing, but more of the relationships. So you have like an escrow, and you have Alice, Bob, and Carol makes a decision. So sort of the computation is very simple, but the relationships are complex, and that's how you distribute keys. So, I didn't focus on that today for a limited time, and wasn't exactly my focus, but definitely for if your model fits into that approach, then absolutely, yeah, that could be great. And my goal is not, to push my project over to anything else. It's just that I think these are all really useful areas of research.
Okay, that's going to have to be the last question. Let's thank the speaker once again. And that's the end of this session. Tarek, I think you'll finish this up.